this is Captain Chaudhari. In my videos, in my series of videos on basic stability calculations, today I'm going to do a few numerical on combination shapes to find out where is the center of pressure. Now let's say there is a combination shape, there is a bulkhead which is rectangular on top, say 8 meters broad, 6 meters tall, and there is a triangle, and the distance of the apex from the base is 6 meters, right? So we can describe this combination shape as a rectangle above a triangle, and triangle's apex is downwards. The height of triangle is 6 meters, the height of rectangular part is also 6 meters, and there is a sounding pipe 3 meters above the tank top overflowing. We have to find out where is the position of center of pressure. Let us say this area is A1 and this area is A2. The first thing to do is to find out the common centroid. The best way to find out the common centroid below the water level, that is geometric centroid below water level, about which we are going to take the moment. We are going to take moment of area about the water level. So for that, the formula is A1 D1 plus A2 D2 divided by A1 plus A2. D2 is this distance from the centroid to the water level. This is D1, and from this centroid to the water level, the distance is called D2, right? So A1 is 48 multiplied by 6, that is from here the distance to water level, plus A2. A2 is half base into height, is 24. And what is the distance to the water level? This distance is 1/3 of 6, that is 2 meters. So 2 plus 6, 8 plus 3, 11. Divided by total area, and the total area is 72 meters square. So let us find out what is the position of common centroid below the water level. So 48 into 6 equals 288 plus 24 into 11 gives me 264 divided by 72. So 288 plus 264 divided by 72 gives me 7.666. So it is equal to 7.667 meters. That is the position of common centroid. Now let us find out what is the total moment of inertia about the water level. Now moment of inertia of rectangle about the own axis will be 8 into 6 cube upon 12. So that is the moment of inertia of rectangular part about the own axis, plus AD square. Area is 48, and D square. D square means 3 plus 3, 6 square. Let us find out what is the moment of inertia of triangular part about the own axis, that is the centroid parallel to the base. The centroid is 1/3 of the height from the base, right? And BH cube upon 36 would be 8 into 6 cube upon 36 plus AD square. The area is 24, and D means 2 plus 6, 8 plus 3, 11. So this is the total moment of inertia about the water level. Divide by total area. Total area is 48 plus 24, that is 72. And depth of common centroid is 7.667 below the water level. Let us solve this. So total numerator would be plus 1728 plus 2904. Total moment of inertia of the rectangle about the water level plus triangle about the water level, divide by 72 into 7.667. That is the depth of COP below the water level. And as is our usual observation, that center of pressure is slightly below the geometric centroid. Let's do one more numerical involving not the triangular shape below the rectangle. Let us have a semicircular shape below the rectangular part, right? So let us see. It's interesting. We will try to devise one golden rule there. Let us see what is the difference compared to a triangle below the rectangle. So there is a semicircle, the bulkhead that we face, water on the other side. This is a combination shape, rectangle and the semicircle. From the diagram you can see that the radius will be 4 meters because the diameter is 8 meters, right? And we had discussed earlier the formula for the centroid of the semicircle from the diameter. So this particular distance is 4r by 3 pi. So in this particular case it will be 4 into radius 4 divided by 3 into 3.14. That is 16 divided by 3 gives me 1.698 meters. Let us also find out the area of the semicircle. That will be half into pi r square. So that is 3.14 into 16 . Area is 25.12. Pi r square is the area of the full circle. Area of half circle would be half pi r square. That is 25.12 meter square. So let's get on to this numerical, and we had said one of the first thing to do is find out the common centroid by taking the moment of area about the water level. So A1 D1 will be 48 into 6. A2 D2 will be 25.12 into distance. Distance is 3 plus 6, 9, 9 plus 1.698, that is 10.698. Okay, because this 6 plus 3, 9 plus this distance is added up, so that will be 10.698 divided by total area, that is 48 plus 25.12 gives me 7.614 meters. So we have the common centroid, common geometric centroid below the water level as 7.614 meters. Let us now find out the total moment of inertia about the water level. Moment of inertia about the rectangular portion about the own centroid is 8 into 6 cube upon 12. 8 into 6 cube upon 12. And when I take this moment of inertia to the water level, it will be plus area into d squared, that is 6 squared. Now, I was telling you the interesting part of a situation where semicircle is below the rectangular area. Moment of inertia about the diameter we know is pi d raised to 4 upon 128, right? Pi d raised to 4 upon 128, and this is something like pi d raised to 4 upon 128, and let us find out how much is this. D is 8 meters, right? So 3.14 into 64 into 64 equals, divide by 128, gives me 100.48, 100.48 meter raised to 4, right? So that is the moment of inertia about the diameter. The question here is, can I jump from here to the water level to find out the moment of inertia for the water level? The answer is no. Now here we are going to learn one very, very important golden rule, that is moment of inertia. When we are using theorem of parallel axis, either we can go towards the centroid axis or we can jump from the centroid axis. We cannot bypass the centroid axis. We cannot go directly from diameter to the water level. Here we don't know what is the moment of inertia about the centroid axis. So first we have to find out what is the moment of inertia about the centroid axis, and that would be found by doing minus AD square. Like if this is the distance d, and how much is the distance d? That is 1.698. So to find out the moment of inertia about the water level in case of semicircle, what I have to do is moment of inertia about the diameter axis minus AD square. How much is the area? Area is 25.12. 25.12 into d square. D square means 1.698 square. So first I have to reduce the moment of inertia to minimum. So I must come to the centroid axis. Now from here I can jump anywhere where I want, 25.12 into d square. So if I want to jump from here to the water level, the distance to jump is 3 plus 6, 9 plus 1.698. So 10.698 square. So following the same rule, that is COP below water level is equal to total moment of inertia about the water level, divide by the area, that is the wet area, multiplied by depth of common centroid. The numerator can be written as 8 into 6 cube upon 12, that is the moment of inertia of rectangular part about own axis, plus AD square, that is 48 into 6 square, taking the moment of inertia to the water level. In respect of semicircle, this is the moment of inertia of the semicircle about the diameter. I cannot take the moment of inertia directly to the water level, so first I will bring the moment of inertia to the centroid, that is by doing minus AD square. Minus AD square means 25.12 into 1.698 square, that is minus AD square. And from the centroid I jump to the water level by doing plus AD square. Plus AD square means 25.12 into 10.698 square, right? So in simplified form I can write it like this: 25.12 in the bracket 10.698 square minus 1.698 square. So the final form, COP below water level, is 144 plus 1728 plus 100.48 plus 2802.63, and this divided by the area, that is 73.12 into 7.614, that is the position of geometric centroid below the water level, and this gives me 8.577. That is the depth of center of pressure below the water level. As you can see, the center of pressure is slightly below the geometric centroid. So this is how we do the calculation for COP in case of a shape that involves semicircle.